Okay, good afternoon, Professor Alfred and all the participants present over here. So today is the third day of our FDP on recent advancement of microwave and millimeter wave communications. So our today's first talk by Dr. Qazi Mohammad Alfred, who is currently associated with Haldia University as an associate professor in electronics and communication engineering department. Some brief introduction about him. He has done his PhD degree in 2014 from Jadavpur University. During this time, after PhD and up to this time, he has authored a good number of research articles in national and international journals and conferences. The research articles mostly based on antenna arrays, communication, signal and image processing, and 5G IoT field. Also, he has a special award which is listed in Marquis Who's Who in the World, and he is also holding patent in his research work, also working on different funding projects by the government and non-government organizations. He is a member. He also are the member of different bodies like IEEE, ING, IRED, and editorial board members and reviewers of different journals and conferences. So with these brief introductions, I'd like to thank Professor Alfred for his interest for giving and talk on this field, which is related to microwave and millimeter wave communication. So I hand over the session to Professor Alfred.
Sir. Thank you. Thank you, sir, for your nice introduction. Very happy New Year to all the participants, my dear colleagues, faculty members, and I am excited to present my talk on the topic millimeter wave, unlocking new disruptions in communication technology, 5G and 6G. So I'm starting the presentation. So the screen.
Yes, sir. Yes, sir.
Okay. So already I am introduced by the respected faculty members of Haldia Institute of Technology. So very good afternoon. So my topic is disruption in communication technology. I am associated with the Haldia University campus. Okay. So the new password is millimeter wave, and also the this faculty development program is the advancement of microwave millimeter wave. So that's why I have chosen a very recent topic, that is millimeter wave, and millimeter wave is going to unlock many new avenues, many technologies, and that is, as you know, disruption means a new paradigm shift in the technological area. So who is just observing or experiencing many disruptions, whether it is computing, whether it is communication, whether it is sensing. We are just observing a lot of disruptions. So millimeter is going to be next big disruptions in electronic communication. So,
Sir, sorry to interrupt.
my presentation.
Sir, sorry to interrupt. Your
Hello.
voice is actually breaking. So can you check your network? Your voice is
Okay.
breaking. So if you have using mobile network, so only
Yeah, yeah,
check the network or you can switch. Okay.
So now is it clear? Hello. Now is it clear? Hello.
Yes, sir. I'd request you to kindly. Yes, sir. I'd request you to kindly turn off your video. So actually, video will taking the bandwidth. So
Exactly,
if you turn
exactly,
off your,
exactly, exactly, exactly,
yeah,
exactly.
yeah, it's okay.
Okay. So now screen is visible. Hello.
Yes, sir. Yes, sir.
Okay, okay. So as I was discussing, that we are observing a lot of disruptions in technological arena in the communication technology. So before starting my presentations, I would like to mention that whatever we are experiencing new technology or development in the device, sensors, communication, digital technology, all due to are the communications. So communications is playing a pivotal role. So we should be proud that we are from communication engineering background, and communication is the driving force for the technology, for developing this technology. So not from today's point of view. So from the very beginning of from around 1900, when Professor J.C. Bose was pioneer in the field of communication. So we have seen that a lot of developments is pivotal around the communication. So without a need of communications, technology is not going to be developed. So again, as you know that microwave was going to be a very dead field in recent time. So there was very little development in microwave and millimeter wave. But due to communications, again there is a new hope regarding microwave and millimeter wave. So always communications is a driving field in our electronic engineering arena. So now my contents of my topic is introduction to millimeter wave. Why millimeter wave? Challenges in the millimeter wave communications, and MIMO and massive MIMO. It's a promising technique. So as you go through this uh, spectrum chart, you will find the electromagnetic signals. So that is 30 gigahertz to 300 gigahertz. This range is actually millimeter wave. Okay, so this is the formal millimeter wave band. What we have studied in our microwave engineering subject. And before that, there is a electromagnetic signals having low frequencies and already occupied by the lot of communication technologies. So now, researcher, scientist, engineer, they are just uh, interested in this area, which is 30 gigahertz to 300 gigahertz. So still, this frequency range is the non-ionizing band. And after that, there is an ionizing band, and this band is very fatal kind of band. There is X-ray, radioactive, cosmic rays, and all these are ionizing band. So there is a in the spectrum, there is a visible spectrum range, that means infrared, IR to ultraviolet ray in this spectrum. So you can see there is it's a sizable amount of spectrum is available from 30 gigahertz to 300 gigahertz. So engineers, scientists are interested in this band. So as the spectrum is congested for new communications, so there is a requirement of frequency band, which is the millimeter, 30 gigahertz to 300 gigahertz. So why it is called millimeter wave? Because if you divide the you try to find the wavelength, you will find that is few centimeter to millimeter will be the wavelength. So very small wavelength. So that's the problematic with this very small wavelength. And the characteristics, development of device, development of antenna, development of communications, there's a little bit difficulties you will find in this spectrum. So as this point of time, we can say this range is this millimeter wave is not so mature, but we are trying to find some space in this area. So now come to the actual spectrum. So as I mentioned that without communications, so the development is incomplete. Okay? So why millimeter wave we are interested? Because the recent buzzword is 5G and 6G and more than that. So this 5G and 6G is going to use the millimeter wave. So now we can get a pictorial view of the millimeter wave spectrum. So is it from, though it is from 30 gigahertz to 300 gigahertz, but 5G communication band is allotted from around 24.25 gigahertz to around 50 gigahertz in this range. Okay, so this is allocated, but in future 24 gigahertz to 100 gigahertz bands will be accommodated for 5G millimeter wave communications. So this is known as 5G NR, 5G new radio. And most important thing is that around 60 gigahertz there is an unlicensed band. Okay, so if you just try to remember that previously we have 2.4 gigahertz of unlicensed band. So that band is so congested, 2.4 gigahertz. In that band we have seen Bluetooth, Wi-Fi, lot of communications are there. So there is no scope for further unlicensed spectrum, unlicensed uses of the spectrum. So 60 gigahertz is providing a new band. Okay, so there is a very new hope that we can use so many unlicensed communication devices. So 60 gigahertz frequency band, and the actual bandwidth is so high. So if the spectrum is 60 gigahertz, it will give you around 14 gigahertz of bandwidth. Okay, so it's a lot of hope is there in the 60 gigahertz band. So in the scientists in the US, in China, they are already trying to develop some chips and antennas in this 60 gigahertz band. So I cannot say at this point this technology is so mature in this area. And so this band 24 to 100 gigahertz band is called FR2 band, that is frequency range 2 band. And before and around 6 gigahertz, this is FR1. This is called the FR1 band. It is called sub 6 gigahertz band. So actually in these two band, that is FR1 and FR2 is allotted for millimeter wave 5G communications. So and this band is called the millimeter wave band, and this is called sub 6 gigahertz band. So as you know, as you all are aware that the recent 5G communication is happening here, that is sub 6 gigahertz band. So from sub 6 gigahertz band to 100 gigahertz band is this FR1 and FR2. It is called 5G new radio. And if you get more look into this spectrum, you can get clear idea that there is a lot of band, that is licensed band at 24 gigahertz. That is a shared band. That is also unlicensed band. Okay, so a lot of bands are there, and it is already going to be allocated in country-wise, US, Australia, Canada, and also you have heard that recently India is also going to sell the spectrum in the millimeter wave. Okay, so due to the new communication, mobile cellular networks, millimeter wave is going to be a new journey. So this is the 5G NR band actually, which I was discussing. So there is a sub gigahertz band. It is around 3.4, 3.6 gigahertz. nearly about 6 gigahertz. It is starting from 24 gigahertz to 100 gigahertz, and also there are up to possibility of 300 gigahertz in the millimeter wave. So now, why millimeter wave? As you know, this is a search of new frequencies. So we scientists, engineers, always there is to be a search of new frequencies, new communication technologies, because there is a scarcity in the spectrum. So it's obvious that there is a scarcity in the spectrum. Incredible hunger of the wireless data bandwidth. Okay, so actually, as per PGPP, they are trying to enhance the data rate or throughput or capacity. It's 1000x, 1000 times. Okay, so there is incredible hunger in the wireless data bandwidth. Wireless mobile data communications, they require EMBB, enhanced mobile broadband. Next is massive machine type communications, that is called MMTC. Okay, so what is MMTC? MMTC means massive heterogeneous devices. That means IoT-based devices will be connected to the network. They will communicate each other. So just you can guess what will be the traffic there. Ultra reliable and low latency communications. So actually, these are three features of 5G. That is EMBB, MMTC, and this is called the 5G triangle. EMBB, MMTC, and URLs. So the network must be ultra reliable. The communication must be ultra reliable. The communication should have very low latency. That means the requirement is less than 1 millisecond of latency. And above all, the more option for unlicensed band. Unlicensed band means it's a license to, it means it's a free to design a lot of communication systems. Okay? So that's why always there is a requirement of unlicensed band. Now, new 6G technologies. Okay, so we are in the phase of in 2022. We are in the 5G phase. Now 6G is going to come. So what 6G will give us? That is a virtual reality. That is V2X communication. That means vehicle to X, vehicle to everything, vehicle to vehicle, vehicle to pedestrian, vehicle to infrastructure. That is vehicle-less communications. UAV. That is unmanned. That is unmanned air vehicle. That is UAV. Okay. So that means recently there is a lot of issues of drone is coming out. So everything will be communicated to the network. Also, there is a new type of communication, that is MEO and LEO, okay, medium Earth and low Earth orbit satellite network, and many more. So again, I am mentioning that all these happening, or all these buzzwords are due to actually communication is the driving force all time. So now, as per my content, these are some challenges. Okay, so we are interested to use the millimeter wave frequency, millimeter wave spectrum, new communication technology, high data bandwidth, low latency. Okay, so these are the facilities and these are the new optimism. So, but what are the challenges? So first we have to cross those challenges. That is propagation constant. Okay, propagation constant is what? So that is line of sight path loss. Okay, that means free space path loss. So as per Free's transmission law, so you know this is the loss component. Okay, this is a loss component. Okay, so as per these equations, so as we take the distance, I have taken some representative values. That is distance is 10 meter. We'll find that at 2.4 gigahertz the path loss is 60 dB. At 5 gigahertz there is so from 2.4 gigahertz there's a path loss. 28 dB path loss is a huge path loss. That means obviously that in micro millimeter will travel very short distance. So it will not cover a large distance, okay, a sizable distance. So it will incur a pass. So that means when we are designing some communication network, cellular network, so we have to consider this path loss. And most importantly, there are some atmospheric losses that in our low frequencies or sub 6 gigahertz frequencies is not affected by this kind of losses, or it is lessly affected, but it is greatly affected. You can see that water vapor absorptions, oxygen absorptions, raindrop attenuations, blockage, foliage blockage, scattering, okay, diffractions. So these are all going to be happen in millimeter wave. And for your information, suppose a suppose there is a millimeter wave source, and if we put our hands at that, yeah, so there will be large obstacles. Okay, so how can we make a communication network? How can we use millimeter wave in the cellular communications? So there is a great challenge due to such losses. And there is a one very important thing I want to just point out, that is scattering effect. Okay. So as the wavelength is very small, okay. So wavelength is in centimeter or millimeter wave. So scattering will be happening. Okay. Just I just take an analogy. Suppose there is a road, okay? And in that road, there is a patchwork is happening. So in that road, who will face most obstacles? Either a bus or or a bike or a auto. So who will face most obstacles? So most obstacle will be faced which wheels are small. Okay, the wheels are large, they will face less obstacles. So that means millimeter wave has very small wavelengths. So they will face lot of obstacles. So the diffractions and scattering will happen, and this will again give some path losses. Okay, so these are the propagation. These are some real challenges that we are going to face, and so now due to this thing, low sensitive to blockages, it is not suitable. It is not suitable for in-loss communications. That is non-line of sight communications. So power will be absorbed. So only it is maybe applicable to the LOS communications. So high detective link will be required. So another challenge is going to be the nightmare, that is higher noise power. Okay, so more the bandwidth, more will be the noise power. K equals to N T B. So higher the bandwidth, higher will be the noise power. So more the noise will, you have to just bear the more noise. So now I'm just going to dishearten you that there are a lot of challenges, but sometimes challenges gives you advantages. Okay. So you have seen in the COVID period, there was no movement, but in the COVID period, there are online classes, online things, that online business, online. So that challenges gives us some some new avenues, new advantages. So millimeter wave is in the same way, they are going to give us some advantages. So what are the advantages? The frequency reuse. Okay. Millimeter wave will exhibit high attenuation in the free space. As they are attenuated in few ranges, okay, so they can be reused. Okay, they can be reused in the cellular network. Why? Because co-channel interference will be less. Okay. So as they are attenuated in very short distance, so we can reuse that frequency because they will not interfere. They will not give the co-channel interference. So it's going to give us a new frequency use. And as it is very lossy, so we have to use some technology that is large antenna arrays, which will give us high gain and high resolution beam widths. Okay. So actually small wavelengths bring technological challenges to reduce component size. So there is also a new. Actually, we can use large antenna with a small area, okay, because of small wavelength. Okay? As the millimeter wave has the small wavelength, so we can use a large antenna array in small area. So that is going to give us a new hope. Okay? So these two advantages will going to give us some sort of relief in network or communication design. So with this with these advantages, a new approaches we may employ in our communication technology. That means wireless communication technology. That is a MIMO. Okay, MIMO and massive MIMO. Okay? The first MIMO, then massive MIMO. So I'm just going to explain what is MIMO and massive MIMO. These are the promising techniques. So in this area, we're going to discuss what is MIMO, what is beamforming, what is phased array antenna. Okay, so actually you have to read this from down to up. That is what is phased array, what is beamforming, and what is MIMO. Okay. So before going to MIMO, before going to massive MIMO, before going to beamforming, I am just discussing one main thing, that is a phased array antenna. Okay, so with phased array antenna, so nothing will be possible. Okay, so first I will just, I think everyone you are acquainted with what is phased array antenna. Just I have to mention that this is a linear phased array antenna. There are n number of elements are there, and they are linearly in the array axis. Okay, so if they are positioned like that, okay, and there is no phase shift in between these two elements, so what will happen? We'll get a beam in the both side directions. We'll get a sharp beam. We'll get a, so sparsely if we arrange the antenna elements, okay, so it will give a narrow high resolution beams in the both side directions. Now, not only we have to form, not only we can feed, not only we can form the beam, but we can also steer the beam. That is our requirement in future communications. Okay, when we are talking about millimeter wave, when we are talking about massive MIMO. So we can see if these elements are having some phase difference in between them, some gradient phase difference, some regular phase difference. Okay, suppose the phase difference is 0 here, it is 5 here, it is 2 5 here, it is 3 5 here. So antenna beam will be directed towards a particular angle. Okay, towards a particular angle. So this direction, that is pi sine theta, in these directions our antenna can be directed. Okay, and normally if we actually why this kind of phase difference is required? Because suppose there is a 0 element and the antenna 0, and you had 0 and 1, antenna 2, antenna 3. So there is a path difference in between. The path difference is d sine theta. So between each element there is a path difference. So if we adjust this path difference gradually, okay, so beam may be directed in these directions. And not only we can make a sharp beam, but we can steer the beam in any direction. So phased array antenna has the key to all the recent technologies. So this is the array pattern. So this is the main beam, and this is a secondary beam. So you can see there is a power difference between the main beam and the secondary beam, and obviously the spacing must be lambda by 2. If the spacing is more than that, so there will be a some grating lobes will be there. Okay, so that is not wanted. So you must require that the spacing must be less than equal to lambda by 2. And I want to just point one thing. Actually, this is the Fourier transform. This is the Fourier. This is a one kind of Fourier transform. It's a space domain Fourier transform. Okay, in Fourier transform, in normal Fourier transform, this is the frequency and this is the magnitude. But here, this is the space. This is the spatial axis, and this is the magnitude. So it's a kind of Fourier transform in terms of spatial angle and the magnitude. Okay. So all the key lies to the without. I just want to those who are faculty member or those who are new researcher, they must learn the phased array antenna techniques. Okay. So without phased array antenna, we cannot design our. We cannot apply those things in the beamforming or in the massive mining. All these things. Okay. So now, before massive MIMO, just this is the MIMO architecture in wireless system. So in MIMO means multiple input, multiple outputs. Multiple input means multiple transmitter antenna, and multiple output means multiple receiver antennas. Okay. So this is our communication path. So there may be obstacle, there may be direct path, there may be two obstacle path. Okay. So actually, the obstacle paths or secondary path or deflected path is causes the fading. So actually, in other communications, we are very concerned about the fading. So fading gives us a lot of headaches. But MIMO is using that fading or using that exploiting those obstacles. Okay. So what they are doing something that is multiple antenna. So whatever it is a phased array antenna, whatever there is a MIMO antenna, whatever there is a beamforming, so multiple antennas are required. So we are going to solve many problems when we are using multiple antennas, the transmitter and receivers. So, so multiple antenna is some going to give us a lot of solutions. Okay. So my point is MIMO take advantage of the multipath. That means multipath is the cause of fading. The traditional radio get confused, but here multipath will be used. Okay. Multipath, MIMO will take the advantage of multipath. So I am coming on that point later. So, so in MIMO there are a lot of things. One is called spatial diversity, and that is called spatial multiplexing. So what is spatial diversity? Spatial diversity means so multipath is a kind of spatial diversity. That means a transmitter antenna may transmit one or more communications to the receiving antenna. So that is not for improving the throughput or capacity. That is just to increase the reliability. Okay, that is just to increase the reliability. So actually, as a human being, we are also using some MIMO. That is, we have 2 ears. Okay, so we are not hearing by 1 ear, but we are hearing from 2 ears. And if you get some experimenting, if you just talk about 1 ear and try to listen all these things 1 ear, and then you try to listen from 2 ears, so you will see the difference. So difference is always there. So receiver also is going to increase the reliability by spatial diversity. Next, spatial multiplexing. Spatial multiplexing means we will use multiple channels or multiple paths. Okay. So multiple channels and multiple path it gives us increase the capacity. That increase the throughputs. Okay. So in MIMO, there are some techniques which we can use, that is space-time signaling, space-time or is known as space-time block coding or Haldia coding, and space frequency block coding. These codings will be used. Okay. For example, in WiMAX or LTE, they are using this kind of coding in MIMO systems. Okay. So now we are talking about diversity. So now just check what is diversity means. Okay. For example, we will send some redundant version of the same signals. We will send same signals. Okay. We will send same signals redundantly. Suppose there are in two time slots, there are two antennas. One time slots, one antenna is sending S1, another is sending S2, and the next time slots, there it's sending minus of conjugate of S2 and it is S1. So S1, S1, S2, and S2. So in subsequent time slots, we are redundantly sending this thing. So what is the need of that? It seems that it is a loss of, it is a wasting of time, but not. It's called the space-time block coding. It is used in mining. Okay, so we are sending same data in same data, same signal in the subsequent time slot. So this will increase the reliability. It will not increase the throughput or capacity, okay, or it will not increase the data rate. It will just increase the reliability, and this is very popularly known as alarm coding in mind. So when we are combining in the receiver, you will see the signal power will be H1 square. It's a very in a standard book you will find these things. That is H1 square or H1 square 2 plus H1. So at least minimum we will get H1 square time of improvement in the boosting of the signal. So that is the reliability. So that is called the open loop transmit diversity. Okay, so this increases the SNR. So in this diversity, no improvements of throughput will be achieved. Only reliability you can. So the next techniques. So before going to the spatial multiplexing, I want to just mention you that beamforming, spatial multiplexing, diversity, they are not equal. They are all you will find in the MIMO and massive MIMO, but they are not equal. There is a lot of difference in between them. But what common is that in between, that in all the cases, multiple antennas are required. Okay. So now spatial multiplexing. So in spatial multiplexing, we need multiple antennas in both transmitter and receivers. H11, H21, H12, H22. These are the channel matrices. Okay, and actually one technique is called, that is pre-coding. Okay, so when transmitter and receiver are communicating between them, so they must have some knowledge about these channels. Okay? So that can be stored in the both transmitter as well as receiver. So in spatial multiplexings, we are using parallel paths, and obviously this will increase the data rate. Okay? So two antenna will increase the data rate 4 times, okay? Or this way we can increase the data rates. So number of antennas we will use, data rates will increase subsequently. So as I have shown, the diversity and the capacity will increase the communication benefits in the MIMO systems. Okay, so that is called minimum transmit receive antenna. We put some plot, we will see the increase, linearly increase the data rate. Okay? And in this graph, you can see, just observe that. So when the number of antennas are increasing, okay. So there is obviously there is increase in the capacity. So at per Shannon formula, you know that SNR is improved, the capacity is also increased. So MIMO has some capacity benefits. So now diversity, you have seen, diversity is not going to increase the capacity of throughput, but it will make the communication very reliable. Okay? So in normal cases, when there is not multiple antennas or MIMO is not there, so there will be fluctuation in the received signal power with respect to the time. So, but with the MIMO, also fluctuation is very small. So, okay, so that is happening in the 4G LTE also. So in the 4G LTE, there are multiple antennas are there, at least 2 into 2 antennas. So that is a quality improvement you will find with respect to the 3G or previous cellular mobile communications. So now come to the massive MIMO. Okay, so massive MIMO is only for 5G is going to be used. So actually, massive MIMO is going to give us 5G and massive MIMO is going to give us three technical directions. Actually, this is the channel capacity that depends on number of access points and mobiles. That is the bandwidth, number of antennas, and signal to noise ratio. So there will be the multifold increase in the capacity and throughputs. Millimeter wave is going to give us spectrum extensions in cellular mobile communications. The network density should be more when you are using millimeter wave. Okay, and it is only spectral efficiency will be increased when we are using 3D massive MIMO receivers. So there will be a multifold increase in the capacity domain. So now massive MIMO will be only successful if we just understand this thing, that is beamforming. Okay. So it is in millimeter wave, the base stations will not be a normal base stations, where the antennas are the sector antenna. Sorry, where the antennas are sector antennas. But in massive MIMO, there is a massive antenna elements will be there. So at least 100 to 1000 antennas will be there, and actually all are phased array antennas, and the number is two-dimensional phased array antenna will be there. Okay, and access points they can cover up to 16 to 64. So now from this picture, it is evident to you that base station is connected with the narrow beams. Okay, with the mobile phones. So how this is possible? Actually, when there is some call is initiated, some call will be initiated, particular user equipment or mobile. Okay, so when the receive power is the maximum, so they will fix a particular mobile. Okay, so actually not only beam forming, beam steering also required. So with this technology, all millimeter wave is possible. Okay, so beam forming is going to play a vital role in massive MIMO. So now there are different kinds of beamforming techniques. So there are analog beamforming, there are digital beamforming, and there are hybrid beamforming. So I am going to discuss what is this kind of beamforming are. Okay. So generally this is analog beamforming. Analog beamforming means the analog phase shifters will be there. So not only analog phase shifters, we digitally controlled phase shifters will be there. Actually, this is a phased array kind of thing. We can just steer. We can just form the beam and steer the beam in a particular RFC. So problem and the conventional Butler matrix, glass matrix, and lens and different analog techniques will be used to beamform. So we can see when the receiver and transmitter beams are matched, the communications will be maximized. Okay. So and the problem is that multiple channel is not possible in analog beamforming. Next, come to the most advanced beamforming. This is called the all digital beamforming or digital beamforming. Okay. So what is the difference between the analog beamforming and digital beamforming? Actually, this is the asymmetric beamforming. When number of transmitter array and number of receiver arrays are not matched, this is called asymmetric beamforming. And asymmetric beamforming is a practical solutions because as is a digital beamforming. So in this area, it's a lot of signal processing is required. Actually, WebDM kind of signal processing. In WebDM, there is a subcarrier is assigned. So subcarrier will be, and there is a multiple signal paths are there. So from here, digital signals, digital processing will be there, digital recorded data will be go to the there. So digital to analog conversions will happen. Now they will go to the transmitter, and depending on the pre-coding here, the particular beam will be generated to the user terminal. So it's a very complex kind of thing. So in a planar array, if you're going to design this kind of beams, so it's a huge, not only a huge in terms of cost, also the computing capacity will be very high, so that you can get digital. So complexity and cost is a main factor in this digital kind of beam. So this type of digital beam programming not in used in 5G millimeter wave. Uh, so next, come to the solution that is recently used, or I just require the faculty members that you start your research if you're going to work in this field, so in the hybrid beamforming. So hybrid beamforming is the trade-offs between digital beamforming and analog beamforming. So in order to reduce the computational complexity as well as the cost, so this kind of hybrid beamforming is used. So recently, a lot of research papers are coming in the hybrid beamforming domain, and actually in 5G millimeter wave cellular mobile scenario, hybrid beamforming is going to be used. Okay. So in hybrid beamforming, one technology is there that is called the sub-array communications. Okay. So instead of use a particular channel, digital channels for particular antenna, here sub-array it is divided between the sub-array. What is sub-array? Sub-array is the array of array. It's actually sub-array is the array of array. So in using some sub-array for particular WebDM channels, it is somehow cost effective and less computational complexity. So the main research focus is now on the hybrid beamforming. So I have seen a lot of research papers daily basis coming on in hybrid beamforming technology. So this is the comparison between three massive memo type techniques, that is hybrid array, full digital array, and obviously, so this computational complexity is very high. So that's why researchers are and the cellular mobile operators are just going to the hybrid kind of systems. Okay. Already I've covered a lot more things about MIMO, massive MIMO, all these things. So thank you for your patience. It's very happy New Year. So thank you.
Hello, sir. Sir, I'm audible. Sir, I have one question. Sir, when you discuss about the beamforming, that is the multiple antenna is used at the transmitter and at the receiver side. So how you means overcome the problem of interference from one antenna to another?
Actually,
that is the coupling effect. How we overcome the problem of mutual coupling or interference?
So there are a lot of problems. We are not only you. I am also working in the phased array antenna for a lot of years. So I have seen there is it's a very difficult situation to overcome all these practical problems. Okay, there is a mutual coupling. So designing orthogonal beams, so beam to beam differences. So these are the practical problems. Okay, and millimeter and this is not really sorted out till now. And that's why informing is a very difficult also in case of massive beam. So until and unless we can get a complete scenario of beamforming technology, so millimeter wave is not going to help us. Okay.
Yes, sir. Okay, sir. Thank you, sir. So now if the participant have some question, you may ask. So participant have any question? They can unmute and they can ask the question to the sir.
Actually, if you have any problem, you can also reach me later. Okay. So you can mail me. You can get my email ID from the organizers. So mainly from Dr. Abhishek Das. And in Haldia University, we have one research group on 5G uh, communication. So we have some advanced softwares and some hardwares also there. So if you have any interest, you can write us.
Sir, in the chat box, some questions.
So there are a lot of actually there are a lot of promising area in internet 5G and massive MIMO. So lots of papers are in daily basis is rolling out from IEEE. Okay, you will find. So new technologies are coming. So one thing. So one question I am getting from Nala Lakshmi, where let me check the question.
The participant may also, that is, I already unmuted from here. You may also ask. You unmute yourself and you can ask.
One question is very interesting. That is where MIMO will be used and where antenna arrays will be used. Sir. So actually, MIMO is multiple input, multiple output. So as you have just concentrated on my discussions, that in when we are using millimeter wave, so millimeter is actually very lossy, okay, and it will not propagate much. So so it will not adaptable for in-loss communication. So there is some fading and all the losses will so there. So only the solution is you can use multiple antenna in that transmitter itself. And MIMO will use that fading effect, okay, actually. So it will not hamper like the other low frequency communications. Okay. So multiple antennas will be required. So that multiple antennas are not a phased array antennas, but when we are coming to massive MIMO, so phased array antenna and beamforming is must. Okay, so that's why I'm telling you. So before going to research for massive MIMO, you must understand the phased array antenna properly. So without phased array antenna, you cannot estimate the beamforming technique because beamforming is vital here. So I think I'm clear. So I will share the PPTs. That is not an issue. So in few days I was preparing the PPTs from multiple materials. Okay, so I'm trying to present the very simple way.
Okay. Thank you, sir, for your valuable time.
Again, one question. In MIMO, what is the maximum possible values of N in TX and RX? Okay. So, and in MIMO, in normal MIMO, that is WiMAX or 4G LTE, it is maximum is 10. Okay. So more than 10 is not required. But massive MIMO is more than 10. Massive MIMO is more than 10. So it's in suppose there are 4x4 at 4x4 MIMO is there, it is sufficient. Okay, so it will increase the 16 times of the throughput. But when massive MIMO is different thing. Massive MIMO is required beamforming. Okay, the very sharp resolution pencil beam will be there. The antenna size will be 16 into 16, 64 into 64. So this kind of resolution should be there.
Yes, sir. Okay. If
So,
any question from participant, any more question?
So thank you.
Thank you, sir. Another question: can we apply power divider concept for a MIMO? Sir, another question.
Okay, actually, power divider is used in the phased array antenna, as you know. Okay, so there are different kinds of feeding mechanisms. People all can get a book. So there is a corporate feed, Okay, normal dividing, all is there. So that will be applicable for massive MIMO. Okay, but in case of MIMO, that is not there's a limited use. That is not required. Okay, but massive MIMO, obviously phased array antenna, power divider, this hardware will be required. So without power dividing, you cannot divide divide the power in different antennas and make a phase shifting, or you cannot control the gain. So all these things you obviously require power divider. Okay. So I request you just get some concept of phased array antenna. So there are a lot of things in phased array antenna. When I have done my research in 10 years ago. So there was no massive MIMO, no MIMO was there. Okay. So only we use this phased array and all these things for radar applications. So now it has become relevant once again. So I am also excited that for beamforming that old phased array antenna and techniques and all these things will be required. Okay.
Yes.
So thank you.
Okay. Thank you, sir, for
Thank you.
presenting a nice presentation, and the presentation is very informative and interesting, sir. And thank you once again for your valuable time from your busy schedule. Thank you.
Okay. So if you have any queries, again I am mentioning that you write to me, okay, and I will help you as per my limitations. Okay, thank you. Okay, thank you, Abhishek. Thank you for the participants for organizing such a wonderful event. Okay.
Okay, sir. Good afternoon to all. We welcome Dr. Bappaditya Roy in our 5-day faculty development program of recent advancement of microwave and millimeter wave communication. Sir, you can mute yourself. Dr. Bappaditya Roy. Dr. Roy, can you hear me?
Hello.
Hello, can you hear me?
Yes. My voice clear to you?
Yeah.
Okay.
Okay. Welcome, Dr. Roy, to our 5-day faculty development program of recent advancement of microwave and millimeter wave communication. So, before starting the presentation of Dr. Roy, I want to introduce Dr. Roy. Dr. Bappaditya Roy obtained his BTech and MTech degree in Electronics and Communication Engineering from WBUT, India in 2008 and 2011 respectively. He obtained his PhD in 2018 from the Department of Electronics and Communication Engineering at the National Institute of Technology, Durgapur, West Bengal, India. Presently, he is attached to Vellore Institute of Technology, Amaravati, Andhra Pradesh campus. He has several index publications, including article in reputed journal, conference, books, and book chapter. Also been involved in a few reputed international conference and seminar as organized committee member. He is a senior member of IEEE. His research areas are microstrip antennas, fractal antennas, and mobile communication. Dr. Roy is the general chair of IEEE conference AISP 2021, AISP 2022, and AISP 2023. He has received many national and international travel grants from Government of India and has traveled abroad for seminar, conference, and workshop. He always welcomes researchers and faculties who want to work in collaboration in the field of microwave and antennas. Dr. Roy, now I hand over the session to you. Dr. Roy, please mute yourself.
Hello, my voice clear to you?
Okay, now it's audible.
Thank you for your nice introduction, and thank you for all your coordinators for presenting this nice workshop, recent advancement of microwave and millimeter wave communications. And this is the one of the best topic on the antenna domain. Okay, so now we can start our presentation. I share my screen. It is visible to you, Dr. Abhishek?
Yes, it is visible.
Okay. I just check pen is working or not. Okay. So now today we are going to discuss about the fundamental of compact microstrip antenna design and its applications. Now, all of you know that what are the importance of the microstrip antenna, especially the slotted microstrip antenna. Here I can use some outline that what is the science behind the antenna and the microstrip antennas, the introductions, analysis of the antennas, what are the fit technique we use, and analysis of slotted structures, and demonstrate the patch antenna and the wearable type of antenna, which is the now the hot topic of the antenna domain. And there is a different technique to design that antenna in or different algorithm we are using for design that antenna. Now, before we start any type of antenna design or microwave, we should know that what are the basic science behind the antenna design. Now let's start our topic of the antenna. First of all, what are the antenna? Now, as a one line, we can say the device which transmit and the receive of electromagnetic wave, that we can call it is the antenna. Now here we are using some parameters, or we can detect some parameters, or we can bother some parameters, which is very useful for antenna characteristics. So main parameter we can consider, that is the gain. Next is the bandwidth. Now input impedance and the radiation patterns also, and the directivity and the center frequency. Center frequency is important for, actually we are designing for antenna for which frequency, and the which bandwidth. So the center frequency, if we know the center frequency, then it is easy for designer to design any type of antenna. Now antenna receive that electromagnetic wave. We know whenever it is used in a receiver end, or it is converted in an electric signal, or it is received the electric signal and radiated the electromagnetic wave whenever it is in the transmitting system. So both cases, when the electric signal, it will convert it, that electromagnetic signal, it will convert it in the electric signal, then it will transmit through the wire or wireless. Now, if we have that electric signal, or if we have that electromagnetic wave, now how we can convert and how it will transmit. Here we want to know the science behind the electromagnetic wave to electric signal. Now we have the electric signal, and how we convert in electromagnetic wave. Now in a closed conductors and a principle of the electromagnetic inductions, we are able to produce a fluctuating electromagnetic field and that electric field around it. Now, however, this fluctuating field around the source is no use in transmitting signal. The electric field here does not propagate. Instead, if it is just fluctuate around the source. Now, in an antenna, the electromagnetic wave need to separate from the source and should propagate from one point to another point. Then only it will transmitting or receiving. Now before how the antenna is made, let's understood the physics behind that, how the wave will be separate from these dimensions. Now here we consider a positive and a negative signal. We just consider one the positive and one negative charge in place a distance, and this arrangement known as a dipole. And it is obviously it produces electric field discharge. Assume this charge is oscillating in a particular point, and the midpoint of the charge, the velocity is maximum, and the end of the path, the velocity is 0. So in the dipole antenna, whenever it will oscillating, we can consider at the midpoint, whenever it will meet the positive and the negative, in the midpoint, it is velocity is 0 at the end of the path, and the midpoint, the velocity is maximum.
Sorry to interrupt you, sir. Your slide is not changing actually.
Not changing.
Mm,
1 minute. Now if I change the slide, it will change.
no, you are not sharing here. Sharing is off right now. Share as a whole window.
Okay. Now my
Go to
presentation.
slideshow. No, go to slideshow.
No, I actually this is on PDF file. I
Okay,
converted
so
it to
just
PDF.
make it full screen, sir.
Full
Just make it.
Okay.
Now just scroll down.
Okay.
Yeah, yes, it's changing.
It is changing now.
Yes.
So where I am stop.
Probably in this slide.
This slide now I think.
Yeah,
Okay. Okay. So next, the charge particles. What are the charge particle? If it is oscillating at the end of the path, the velocity is 0, and the midpoint, the velocity we can consider the maximum. Now, this charge particle, if we continuously doing now some acceleration and declarations due to the velocity variation, it will be happen. Okay. Can you see my full screen?
yes. Okay.
Okay. So now you can see that due to the acceleration and the declaration, that velocity is changed. Okay. Now now the changes, it is find out how the electric field vary due to the movement. Let us consider the one electric field line. These are the electric field line. If we consider, one is the positive charge, another is the negative charge. Now consider the electric field line, the waveform at the time equal to 0, that time equal to 0, it will expand more, and it is called the more expansions, and it is deformed at the time equal to t equal to t by 8 time period. So now if we consider that the t equal to 0, that will extend and it is deformed at the 1 by time period, then we can easily calculate the how much time it will require for one accelerator and one uh, acceleration, and one is the changing the velocity. Now you might be expect the simple electric field discharge in the one locations. So now every time period 0 to t by 2, it will starting from the plus and ending the minus. So it will the expanse in the t equal to 0, and when is the maximum in the t equal to 1 by t, then it is deformed. Okay. Now both acceleration and the declarations change accordingly, and it is produced that one electric field. Now produce some electric field with some memory effect also there. If we continue with this analysis, then we can see how the 1/4 wave will be generated. Now you can see in this figure here in the t equal to t by 4, what is the structure? After a certain time, it will release from one memory element. So it will continuously in the same manner. We can see there is a 1/4, that is t equal to t by 4 time period. The waveform meet at a single point. After that, it is separate and propagate in the line. So it will continuously transmitting from one point to another point. Now this varying electric field automatically generate that magnetic field which is perpendicular each other. Now it is interesting to show that the wavelength, from the one separation to the full acceleration, it is required that lambda that will equal to twice into L. That is double length of the dipole. And this we really need for the one antenna designer. So that's why for antenna designer, they want that lambda that will equal to twice into L. And what is the L? L, the starting point where that 2 point plus and positive charge and the negative charge both are the joint. From here to the last ending point where the propagation will start, means propagation is performed, that is equal to the twice into L. Now if we make this arrangement for oscillating in a positive or the negative charge, we can make an antenna. To produce this positive charge and the negative charge, we can use one rod where we can use that acceleration and the declarations. You can see this example in this slide. Here we are using that one center rod where the positive and the negative charge both are there, and it is pointing the positive and the negative charges on both sides. We take a conducting rod, we take bend in the center, and it is apply the voltage source at the centers, and assume this is the signal we apply. Okay. Now at the time varying the voltage signal, we consider at the time 0, due to the effect of the voltage, the electrons is displaced on the right side of the dipole, and the electron, the negative charge, that will be stored in the left side. So we consider that left hand side, it is lost the electrons, and the right hand side is accumulate the positive charge. So these are the total rod. Here we bending in the middle or centers. Now if we apply the voltage source through the rod, the positive charge that will be stored in the right hand side, and another charge that will accumulate in the left hand side. Now if we see the antenna as a transmitter, then it will work the frequency for transmitting from one point to the another point. Now the frequency of the transmitting signal is sum of the frequency which is applied in the voltage signal. Since the propagation travel from speed of light, we can easily calculate the wavelength of the propagation. For the perfect transmitter, the length of the antenna, it is 1 by 2 of the wavelength. Now the antenna operations and the antenna which is the receiving signal, both are the opposite. So whenever the antenna uses this transmitter, they transmit the signal from one point to the another point. If we apply the voltage source like that, and it will you can calculate the frequency in terms of voltage. But that opposite case whenever it is used in a receiver end. Now at this instant, if the electron accumulate at the end of the arm, now the applied electric field vary the positive and the negative charge is accumulated at the other end. Now the varying electric field or varying the electric charge accumulate means it is varying the voltage signal which is produced here, and that voltage signal at the center of the antenna, it will change the positive charge and the negative charge. Now the voltage electric signal of the output when the antenna is a receiver. Now the frequency of the output signal is the same as the frequency of the receiving electromagnetic wave. Now it is clear from that electric field configuration that perfect reception, the size of the antenna, it will require the L equal to lambda by 2 or lambda equal to L by 2. Okay, so now these are the one example of the rod type of antenna. Here if we apply the voltage source in the center, now the positive charge which will be accumulated in the right hand side and the negative charge it will be accumulated in the left hand side. Now you can see the previous structures where the positive charge and the negative charge meet in the single point. After certain time period, it will release from here to here. So it will act as a transmitter, and the opposite case it will act as a receiver. Now let's see a few cases where we are use that antenna which will be perpendicular for the transmitting and the receiving. Now here we are using the one rod type of antenna where it is bent in the center point. Now here we apply the frequency. Suppose here we apply the frequency V with voltage V, then the positive charge accumulate in this side and the negative charge accumulate this side. Now after the time period T by here lambda time, when lambda equal to twice L, then that will release from this positive charge and negative charge, and it will continuously oscillate with a electric field and a magnetic field. Now let's use a practical antenna. It is how it is work. Now there is a one practical antenna. We can consider the one rod type of antenna or ECE type of antenna. Here we are using the varying voltage signals in this end, that is the input impedance, and entire length we can consider the L equal to lambda by 2. Now if we apply the voltage source, it will act like that. It will transmitting the voltage source like that, and one end it will be received. Now we are apply the one basic practical antenna. These are the antenna we can see in our household applications, but nowadays we are using the DTH, but previous time we are using that type of antenna. Now this type of antenna practically we can use, and now we can discuss how it is work. Okay, in the first, a dipole antenna is used in the TV receptions. A dipole, it is receive the signal, and one reflector is there, and another director also available. Now for this type of antenna, we use one the antenna that is ECE antenna, one reflector, another is the director. Also it needs kind of the antenna one wire which will be connected from the antenna to down. So these complete structures we can call as a ECE antenna, where the signal it will receive in this dipole, and through these reflectors the signal it will be comes to the house and hold, and then we can receive that signal, where there is a two lobes are there. One is the major lobe and other two are the male lobe. Now here if we replace that antenna, then it will be reflected like that. Now the dipole antenna, it will convert the received signal into the electric signal. These are the dipole antenna. This dipole antenna, it will convert the electric signal, receive that signal into the electric signal, and this electric signal passes to the coaxial line to our TV unit. Now the TV will be continuously receiving the signal and transmitting the signal. The transmitting time just opposite work. Whatever we want to transmit from the broadcast area, that will be frequency that will be converted in a electric signal through the wire, and now after the electric signal it will convert it again electromagnetic wave or EM wave, then it will be transmitting through the air. But nowadays we are using the DTH. We are using the dish TV or dish antenna. It is consist of the two components. One is the parabolic reflectors. Another is the LVNF, that is called the low noise LVNF. Sorry, LNVF, low noise back converters. Okay, so one parabolic reflector is there, another is the low noise back converter. Now the parabolic dish receives that electromagnetic signal from the air or from the satellite and focus on the LNVP. Now LNVF, it is made of the feed horn, probe and the waveguide PCB. Okay, so here in the inside the LNVF, whatever the signal that received from the satellite, that signal that will be processed through the LNVF. Total signal will be processing through the LNVF. Low noise signal, low noise back converters. In the low noise back converter, that will consist of some probe, feed horn, and the PCB and the waveguide. Now the incoming signal focus from the probe, and at the probe the voltage is induced as we see in the dipole cases, and the PCB inside the LNVH, the PCB used for the signal processing. Signal processing means that is the filtering, conversion, high to low frequency, low to high frequency, that type of applications done inside the LNVH. Now after the signal processing, the electric signal carried from coaxial cable to our TV unit. Now it is see what are the structures of the LNVF and how it is worked. I just show here one slide inside the LNVF. Now as we already mentioned that LNVF, it is work for the signal processing. Signal processing means that is the filtering, conversions, high to low frequency and its applications. Now after signal processing, the electric signal carry using the coaxial cable to our TV unit. Now you can see inside that LNVF, that structures, there is a two probe. The probe arrangement is the perpendicular to the each other. Here is the two probe is there. I can show you the next pictures. Here you can see the two probe is there. One is the perpendicular vertical pin, another is the horizontal pin. Now this arrangement, it is perpendicular to each other. That means the available spectrum, whatever the spectrums is available inside the wire, that use the two types. One probe detect the horizontal polarizations and another probe detect the vertical polarizations. You can see the polarization structures in the previous slide. In this previous slide, you can see there is a two signal is there. One is the vertical line, another is the horizontal line. So that probe LNVF made like that, where we can detect that horizontal signal as well as vertical signal. That's why nowadays the DTH is very important, and we can take the clear pictures, or we can get that more frequency, or we detect the more frequency, whatever the frequency or whatever the spectrum available in the air. Now the one probe, it is detect the horizontal polarizations, another probe is detect the vertical polarizations. Okay. Now this type of antenna are not suitable for personal applications because it is the bulky. This type of antenna is bulky and it will detect the more frequency, and arrangement is required more because parabolic reflectors require, LNBF require, wire require. So for personal use, we are not use that type of antenna. So we are using that one small antenna that is called a microstrip antenna, which is used in a mobile phone. It is very specific, and aerospace applications also. Why we use that microstrip antenna? Because it is the lightweight and it is very easy to fabricate and easy to carry also. Now the cell phone capacity use different type of antenna. It is called the one antenna. It is called the patch antenna. Okay, so the patch antenna, it is consist of the dielectric materials on the ground plane, and the metallic patch act as a radiating element, and in between the radiating element and the ground plane we are using the substrates. Okay, now we are coming to the main things. What is the microstrip antenna? Just now we just discussed about the main physics, how we can how an antenna will work and how the propagation will be made. Now the microstrip antenna or the patch antenna, inside the antenna, how it is looks like. Now as we know, as we already discussed, that why it is the lambda by 2, that we already discussed in the previous slide. Now for designing any metallic structures, we are considering that whose length it is lambda by 2, where the top surface we can consider the metallic surface, it is considered the radiating elements, and the opposite is a ground element. In between patch and ground we are using the one substrates. Now in the simplest and the widely used microstrip antenna, which is shown in this figure. Now here we are using that one coaxial feed antenna along with the coordinate systems. Here the coaxial line is there, and the height between the substrate and the ground plane we consider the h. Now there is a one famous formula for calculating that reflection coefficients and others materials also. Now a rectangular patch is defined by its the length and the width. So we consider the one length and another is the width. So that a length and width we can calculate using the very famous formula is there available. We can calculate using that formula. Now at first we first know the what are the center frequency, f. How we can calculate the f? If we know the l, which length required, then we can easily calculate the frequency. Now as we know, the rectangular patch antenna is defined by its length and the width. Now the width is comparable with the wavelength to enhance that radiations of the antenna. Now the substrate thickness is much smaller than the wavelength, because substrate is the very important, and substrate thickness is the smaller than the wavelength. Now for the fundamental of TM10 mode, that fundamental of TM10 mode, we are considering this mode, fundamental TM10 mode, the length L should be slightly less than lambda by 2. Okay, you must remember in the fundamental mode, we are considering the length is slightly less than the lambda by 2. Where is that lambda, that will actually equal to the lambda naught by epsilon. Okay. So here the lambda, that will equal to lambda naught into epsilon. Where the lambda naught, it is the free space wavelength, and lambda naught, it is slightly less than, and lambda naught, it is called the effective dielectric constant of the patch. Now the value of epsilon c, it is slightly less than epsilon r, where is the epsilon r is the dielectric constant of the material. Why the epsilon c is less than epsilon r? Because of the fringing field around the periphery of the patch are not confined in the dielectric substrates. However, for thick analysis or design approximation, we are using the epsilon used in a particular epsilon c, we are used less than epsilon r. Okay. Now in the patch, we are excited using different feeding technique. Here we are using the different feed technique for patch. First feed technique we are used here, the line feed or planar. Next one is we can use the aperture feed. Next one is we can use the line feed or coaxial feed. So there is so many feeds are there. Now if we consider the fundamental mode of microstrip antenna, where you can use the any structure, plus structures or this structure, any type of structures. But every antenna for exciting, we are using different type of feed. Okay, my slide is changing.
Yes, sir, it is.
Okay, so now a patch excited by microstrip line feed, which is shown in this figure A. So in this feed arrangement, as a one advantage is there, it can be each on the same substrates because it is the planar. So the total structures, it is remaining planar. But there is main drawback of this type of structures. The main drawback is the radiation from the feed line. If it is the planar structure, you can see this part we can consider as the radiating element, and it is planar. Then there is a main drawback where radiation from the feed line, which is lead to the increase in the cross polar level. The next is the thick stubness. Suppose we are using the thick substrates, we are which is generally employed to achieve the broad bandwidth. For this type of microstrip feed, increase in the substrate thickness to increase the width, which is turn the increase the undesired feed radiation. Okay, this type of structures also we can use, but if we consider the thick of substrates, more radiation from the feed line. So that is the main drawback of this type of antenna. Another type of antenna, that is the indirect feed place between the patch and the ground plane. These are the indirect feed line which will place in the between ground plane and the patch. Now, which is separated by the two dielectric material. This type of feed we can separate by the two dielectric material. Now here one advantage is that the feed network radiation is less, but here main problem we are using the double substrates, which will more costly, and it is lead to the fabrications. So there is another type of problem for this type of structures, because here we use the two dielectric material. Main advantage is the configurations. It is feed network radiation is there, feed radiation is less, bandwidth more, but main problem that two substrate we are using. If is there using the two substrate, maybe the air gap is there. So there is another drawback. Now another method we are using, that is called the aperture couple configuration. Now for aperture couple configuration, the field is coupled from the microstrip feed line to the radiating patch through an electrically small aperture cut on the ground plane. These are the small aperture that will come from the ground plane. That's why it is called the aperture type of feed. Okay, this resonate slot, this provide the another resonator, that is the additional one. Okay, so if we cut from this ground plane, this resonate slot provide another resonance in addition to the patch radiation. In results, that will increase the bandwidth. That is one of the main advantage for this type of aperture. Another one, the propeller feed technique or waveguide feed. It is also used in a different type applications, different designer. In this method, the propeller waveguide feed is each on the ground plane, and the line is excited by the coaxial feed, is terminated by the slot. So these are the called the propeller waveguide. The main disadvantage of this method, it is high radiation from the longer slot. These are the slot. Suppose these are the feed line. Here we cut the one slot. Here also we can cut one slot. The main disadvantage of this method is high radiation from the longer slot, leading to the port to back ratio. These are the one of the main drawback of this type of feeding technique. Now, if we use the CPW feeding technique, there is a one question is coming: what is the polarizations? If we use that any type of feed technique, what happens the polarizations? Let's see the one example of the polarizations in the CPW cases. There is a two type of polarizations is there. One is the linear and other is the circular polarizations, which is possible for any simple feed. Now, for polarization definitions, that is actually the determined by the orientation of electric vector with time. That is actually called the polarization. Now, in these pictures, you can see here that electric field that will perpendicular each other, that will already discuss in the introduction slide. Now here we are using the two polarization. One is the horizontal polarizations, another is the linear polarizations. One polarizations we can call the left hand side, another is the right hand side polarizations. Now before that, we first consider what is the polarizations and what is the linear and what is the circular polarizations. Now polarizations means that is determined by orientations of electric vectors with time. Now if you want to circular polarize, no need to change that dimension of the patch. If we simply change that feed technique, then the polarizations can be changed. So polarization is the one of the important part of the antenna structures. So any researchers, you can see they are changing the feeding point or feed structures to change that polarization one point to another point. Now the dimension of the patch only we can change of the feed location. Without changing the dimension of the patch, we just changing the feed location. Now the electric field, it is looks like this way, or it is like this way. With respect of time we can consider this way or this way. Now the orientations, what is the orientations? The orientations of the electric field is remaining change with repeat to the time. It is called the linear type of polarization. So what is the linear polarizations? We know from these pictures we can see the orientation of the electric field remaining change with respect to time. It is called the linear polarization. Whereas that polarization, suppose the polarization is starting point here t equal to 0, after t equal to time t equal to capital T by 4, the position is here. Now after t equal to pi by 2, the position here. Now continuously it will moving from one point to another point, from the left side to the right hand, then it is called the circular polarization. Now the orientations of the electric field, where the polarizations, it is t equal to 0 in these positions, after time period, certain time period, the electric field vector is changed and rotate in another place, it is called the circular polarization. So main notes here, the electric field vectors compute the circular rotating from one to another point and magnitude remaining the same. It is called the circular polarization. Now next, there is some feeding techniques. Here another feed technique is there. We can consider this as the inside feed technique, where we cut some slotted from the patch and we can post that antenna inside the patch structures. That is called the insert feed antenna. Now next, now antenna length we are already mentioned here. The antenna length we consider the lambda by 2, and this length control the resonance of the frequency, and other length it is control the bandwidth. So here the length L equal to lambda by 2, it is control the resonance of the frequency, where W that will control the bandwidth of the frequency. So here substrates we are using now another main important is the substrates. What is the substrate? The substrate actually it will separate from the patch and the ground plane, and the substrate used only for the metallizations, and we can use any type of substrate in the antenna. So some of the characterizations is affected if we substrate is lossy. Now the dimension of the antenna, it is lambda by 2, and this lambda, this not the wavelength in the dielectric. So the lambda that will equal to lambda naught divided by root of epsilon r. where lambda naught it is the free space, and lambda r that is called the dielectric constant. So some presence of the substrates, we can make the antenna as a compact. But at the same time, if you want to go for the increase the epsilon r, suppose if I increase the epsilon r, then it is make the smaller and smaller of the antenna size. So antenna length, it will depend on the lambda. Now if we increase that epsilon r, the lambda will be decreases, but we can't do that. The reason behind that, there is a one fringing effect inside the here. So if we go for the epsilon r is more, then the lambda is decreased. Now it will determine the fringing field. When we excited the antenna, there is a going some sort of field between the top metallizations, these are the top metallizations, and the ground plane. That is called the fringing field. Now the larger fringing field, which is responsible for the radiations. Now, if we consider these are the top metallic and this is the ground metallic. Now, if this height is more, the fringing field is more. Okay, the larger fringing it is responsible for the radiations. Now, at the end of the radiation, here in the side, if it is more, the radiation is also more. Now, the dielectric value is less, then fringing field is increased. So, if the dielectric value is less, the fringing field is increased. We should have the more and more fringing field because we need the more radiations. So we should use the dielectric value is less for the more fringing field. So we use that epsilon r that will equal to 1 to maximize the radiation. So for maximize the radiations, we should use epsilon r equal to should be low or h should be high. This is for the antenna design. But for the circuit cases, it is just opposite. For circuit design, we are using the height is less, the thickness is low, and epsilon r is more for these circuit applications. For antenna applications, we are using the epsilon r should be low and the substrate height it should be low. Okay. So these are the for antenna basic structures and basic things. Now for choosing the appropriate material, is the primary of the antenna design of the microstrip antenna, because substrate selection is the primary important and for the design, or it is prime importance also. This is because so many limitations can minimize, because the high return loss, low gain, low efficiency can be overcome by the selecting the appropriate substrates. For fabrication of the antenna, without changing the resonance frequency, the substrate properties such as the dielectric constants, loss tangents, or others we can change this. These are the one importance of the substrate. Now coming to the main few applications, here the one advantage and the disadvantage are there. So I am not discussing about that advantage and the disadvantage. I just go for the basic applications. Here one structure is there, basic structures, where one patch antenna is there, where 15 is the length and the 12 is the width, where the ground size just double of the patch size. And here we use the feed line, it is 25 mm. Now there is a one basic structures is there, where these structures you can see where we are using just coaxial feed line in the middle of the structures, and we are introduced the two slotted, this is called the closed slot, two slot inside the patch, another two slot we are introducing the ground plane. Now here the simple patch and here the slotted patch is there. Now both patch if we simulate, then what is the changes here you can easily find out. So this antenna it is working for the 5 point, this frequency 5.2 to 5.8 in the wireless frequency band. Now the green color, you can see the green color is the final antenna where the 4 slotteds are there, and the black color without slot, only the simple patch. So there is so many changes in the radiation or reflection coefficients. Here some highlighted are there, result highlighted, where antenna 2, antenna 3, antenna 4 are there, and antenna 1 you can reference antenna. Antenna 2 where we use the 2 slotted, antenna 3 along with 2 slot we introduce the another slot in a ground, and antenna 4 there is a fully 4 slot are there. Next, another type of U slot antenna where we are using that one A structure inside the just back view of the antenna in the ground plane. Now you can see that these are results entirely change of the black color. The black color is the reference one antenna result, and the green color it is the final antenna. It will belongs from the 3.22 up to 6.2, where gain also increase in this frequency band. Now, why I use the substrate is the prime important, because substrate is the important. You can see from these results, same structures without changing the any feeding, any feed technique, without changing the any dimension, without changing the any positions. We just change the substrates. We can change the Teflon to polyimide, polyimide to PCB, PCB to backlight. Now you can see easily what is the changes in the S11. The red color, it is used for the FR4, where entirely change. FR4 we can use the best results where dielectric constant is 4.4, where other dielectric constant is less, but it will not good result. Okay. These are the same structures where, but here we are using the multiple number of substrates. There is a more than 2 or 3 substrates we are using here. So what are the changes here? As we discussed in the few slides, what are the effect if we use the multiple number of slides? If we use the aperture type of feeding technique, we use the 2 or 3 substrate is there. Here one example with coaxial feed where 3 substrate is there. The main middle substrate we are considering the lambda equal epsilon r equal to 1, where top epsilon that will equal to 3.2 and the last one is the 3.1. Now these are the another antenna which is published in the that LAPC. These are the one type of monopole type of antenna. Simple we are using the one slot in the ground. The entirely result will change. The result you can see from here. The entirely result will change whenever the D you can from here. It is 3.5 mm. So these are the all slotted type of antenna, and using the different, we also vary with the different substrates and how it is work. Now these are the one of the soon to be slotted type of antenna where multiple number of slot same structure replaced in the antenna. In the back side, in a ground plane, we are introduced on the dumbbell side of slot in a ground plane. Now these are the hexagonal antenna, and this type of structure is very useful for the UWB antenna, where hexagonal you can see the all dimension are same, where we use the 2 square type of circle inside the antenna. This is called the one type of planar type of antenna. Here the bandwidth is more, whatever I discussed in the last slide, that bandwidth can be more, but this type of antenna, the radiation from this patch, it will more. So the radiation, lack of radiations, we are not use that type of antenna, but the bandwidth, obviously this type of antenna is more. Another type of structures where results you can see these results, and these structures, one of the circle structures, inside the circles we are using that another square type of slot, and after the square type of slot we are introduced the another radiation patch inside the circle slot. Now entirely result will change. Here this type of antenna mainly used for the notch type of frequency, or here we are using, where we find the 3 notches. First notches we can find out in between the 3.5 to 4.5, where second notch it will 5 to 6, and the last notch it will 8.5 to 9.5. Now we are a designer, the scientists, they are not design only antenna for radiation or only for the UWB antenna. Also we are designing the antenna for the notch frequency. Why the notch frequency? Because few frequency are not required for application. So we are we want to notch that part for changing any structure inside the patch. We are showing here all the slotted type of structures. Here A11 versus frequency plot, you can see decoupling structures is there, where one structures you use inside the structure we are using the U slot, and the back side you just use that I type of slot. So this type of slot we can call the decoupling type of structure. And these are the one antenna where we can use the four patch antenna inside. These are the four patch antenna we are used here, and uh, we are using the Butler matrix inside the patch and the simple patch structure we are using. Now, what are the use of the Butler matrix? Depending on the matrix, we can calculate what are the frequency or what are the S1 parameter for each. We have discussed here the S11, S21, S21 and S31 here, and the all patch dimension is the same of this Butler matrix. Now the coming to the main next one, that is the wearable type of structures. Nowadays these are the very hot topic, that wearable antenna. Even medical purpose we are using the capsule type of antenna. Suppose the endoscopy or other cases, one of my research scholar they are doing research on the endoscopy, capsule endoscopy. So this type of small antenna, no need to check that endoscopy from the wire. If any patient, if they take the medicine like a capsule, the entirely stomach pictures we can take. That is the wearable type of antenna, and capsule endoscopy is called. Another type of wearable antenna, it is used for the military purpose mainly. We are using our antenna in our cloth or in our shirt bottom. So this small structure, small antenna, that will be detect that frequency, GSM frequency as well as high frequency also. So here is one example of the wearable type of antenna, and we tested this antenna in our own cloth. These are another type of jeans materials. We are using the jeans material. This antenna we are designing. So using jeans, we can design one slotted antenna. Now this will perfectly match where we can place. It is the free space, chest, waist, and the leg. Wherever we can place, it will perfectly work. So we can demand this type of antenna. It is useful for wearable where the gain is more than 6.5 and that bandwidth it is 2.4 to 14.88. This is recently published in the Radio Science Journal. Now the last topic, that is the design part, how we can design. Now coming to the questions, why we are using the slotted antenna and how we can design, how we can confirm that which length is suitable for the which frequency. So there is a famous tools are there. One is the genetic algorithm or PCO or the practical swarm optimizations. Doing the optimization technique, we can calculate the frequency or we can calculate the length of the antenna. So there is a two type of technique mainly we use. One is the PSO technique, another is the GL technique, genetic algorithm. Mainly these two techniques we are used for the optimizations, and using optimizations we can calculate the perfect structures. Optimization means it is to make the perfect. So we can optimize that structure. So we can optimize that frequency. We can optimize the length to know the better parameters. Now here one example is done. Here we are using the PSO technique and the genetic algorithm for same on the same structures. You can see why we are using L equal to 48 and the width equal to 41. Using the optimized technique, we consider what are the optimized values. The basic dimension, you can see this is the 48, the basic dimension 48, whereas our optimized dimension is 47.56. So how accurate it is? Here it is, the basic parameter is 41. Now the optimized parameter is 41.3. Now using optimizing technique, we can easily detect the antenna length and the width, and we can design that specific structures for the specific applications. There is some process for practical optimizations, how we can do the practical optimizations and where we use. So there is some process after practical optimizations. Here you can see the results. These are the optimized antenna gain, where is the without optimizations the normal structures gain is there. Now you can see the gain of the optimized antenna. It is maximum, it is 3.8, where without optimization the gain is very less, where the VSW are also same patterns. So these are the one of the useful technique to know the actual antenna or actual structure. Okay, these are the another applications where we can use for antenna. Now, how we can use the genetic algorithm for the monopole design? There is some steps. If we use the initial populations, first we take the initial populations, first we evaluate the fitness. If we satisfy, then we can go for the antenna structures. If we not satisfied, then we can again use for the evolution fitness. So these are the technique, and here some code is there how we can use. Suppose we are dealing with that different type of substrates. Which substrate is best for this structure? How we can know? Using genetic algorithm, we can find out that which substrate is useful for this monopole antenna and for the particular structures. And these are the summaries for microstrip antenna technology. Nowadays up to 65 gigahertz, and one of my research scholar, they are design 35 gigahertz up to 1.1 to 35 gigahertz, and the size of the structure is very low, and it is flexible type, and capsule type of antenna can design. And the antenna, it is useful for millimeter wave, 5G applications, 6G applications. Nowadays it is demand more in the medical applications also, and for high power applications we are using the antenna. So that's all from my slide. In the short time, I try to cover the antenna structures and the physics. Now, if you have any query, you can ask.
So thank you, Dr. Roy, for your nice presentation. The presentation is very informative and interesting way you present. So now if the participant have any question, they can ask directly to Dr. Roy. So first of all, I want if any participant want to ask any question, they first mute themselves and then can directly ask to Dr. Roy.
If you have any doubt, you can ask. Otherwise, you can note down my mail ID. If you have any query, you can mail me.
So one question, Dr. Roy, in the chat box asked by Anupama Chaurashia. And so she asks how different shape are decided for any particular application.
Okay, that Anupama is next question. How different shapes are decided? Actually, shape we can't decide it. We can detect that we can fix that antenna length and width using the center of frequency. So if we fix that frequency, then we can decide that width and length. After width and length, we have to check what are the desired frequency, then we can change our shape. So shape is not important. Main important is which frequency you want to design.
Anyone have any other question? They can ask.
One question here: how different shapes, sir, which substrate would be much suitable for 5G applications? You can see there is a for fringing effect, to avoid the fringing effect, to avoid the radiation losses, we try to use that low height or low dielectric constants, and height is more. But for physical purpose, suppose we are designing one antenna, that antenna is not suitable for our mobile phone, so that is not good. So always our aim to our providers, means antenna designer or company, their demand. So substrate, you can use the FR4, or you can use the Teflon, or for 5G cases we can use the gold also. But for expensive cases we are avoid the gold. Better we can take the any substrates where thickness is the less and the dielectric value is less than 5.
Okay, no more question. So I have one question. That is when you optimize the microstrip patch antenna, that is the suitable cost function is required. So how you mathematically model the
Actually, mathematically model, we have some mathematical proof, means the MATLAB coding. Suppose we don't know the which substrate we are using. Okay, so using that genetic algorithm, if we put that some values, suppose here the dielectric constant is 4.4, we fix the 4.4 to 3.5 or 5.5, and we fix that frequency. If we fix the frequency now using the coding, the MATLAB code, we can find out that exact dielectric constant. So suppose the result is 4.5, but 4.5 dielectric constant is not available. So we can take the nearest value of the 4.5.
Okay, 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 thank you. So another question from K. Srilata.
What is the
She
name of
asks,
the software used to design the microchip antenna? There is so many softwares. You can use that. My one scholar used IE3D. Another two scholar, they are using the CST and HFSS. You can use that any software. I just write in the chat box HFSS or I just write in the chat box. You can use any type of software. If you need any help on this software, you can mail me. I will contact with my scholar to you. They can help you.
and if there are any, if anyone fabricate any patch antenna, is there any availability for measurement in VIT FD?
Yes.
Okay, measurement facility or anechoic chamber is.
Measurement facility is there, and but depend on the structures and depend on
Okay,
the frequency.
thank you. Anyone have any other question, participant? So no question. So thank you, Dr. Roy, for your nice presentation, and thank you once again for your valuable time you give for the FDP program from your busy schedule. Thank you.
Thank you. Invite me.
So thank you all participants. So today it is the end of the session. So tomorrow the FDP will start from 2:30 p.m. Thank you all.